It's my pleasure to be able to introduce the final session from this morning's Game On Spring Data Science Festival. And I'm introducing Eyal Kazin from Zimmer Biomet. He's going to be talking about causality, mental hygiene for data science. Eyal is a data scientist with 20 years of experience, coming from a background in cosmology originally. He simplifies complex problems and transforms data into clear, actionable insights. He's passionate about using visual storytelling, methods from statistical inference, and machine learning to deliver practical solutions, and helping stakeholders make data-driven decisions by communicating their impact in a meaningful way. Over to you.
Thanks for that, Charlie. Thank you. Hi, good afternoon, everybody. I realize I'm what's separating between you and lunch. Hopefully, this will be engaging and informative. Just before I start, I do want to point out the link on the right. You have access to all the slides anytime you want, so feel free to take a look. And I would like to start just to have an understanding where people are on their causal journey. So just a quick raise of hand, whoever this is the first intro talk to causality, the first time that you're learning about the topic. Okay, great. And on the other side of the spectrum, how many people have started to implement causality within their workspace? Okay, great. So yeah, there's probably a lot of people in between. So for those who are newcomers, well, welcome. Hopefully this should be the beginning of a fascinating journey. For those who have experience, I hope to shine light on aspects you might not have considered in the past. Causality has been gaining momentum in the past few years in machine learning and data science circles, but as opposed to deep learning, which we experienced a decade-long boom of transformative applications, and causality hasn't had its spark moment, right? We're not seeing the headlines as we do see, for example, with large language models. And the first question that raises is, well, why is that? And in my humble opinion, the reason is it's because causality is not plug and play, but rather what it requires is it's not plug and play because we're not just optimizing for metrics. Actually, we're rethinking how we frame problems altogether, and by so we can get deeper level of engagement with our data. That manifests, for example, in the fact that even seasoned practitioners will find it challenging to apply causality in real-life circumstances. And if you're a beginner or an aspiring data scientist, then you rightfully can question, is it worth my while to dedicate time to climb the so-called causal ladder? I like this post that came out a few days ago in LinkedIn, in which Chelsea here points out that learning causal, that she does recommend everybody to learn causal inference. And she also points out the fact that in many circles, a lot of us who learn analytics, they're not even told about analytics. Earlier this morning, I spoke to somebody, I talked to somebody about this talk, and he immediately asked me, are you an economist? Because mostly economists get trained these things, and the rest of us have to figure it out on our own until they're exposed to a talk such like this. And so I'm going to reinforce what she says here, and I'm going to take it even one more step, and I'm going to say that regardless, just assessing if causality applies to your work, even if it doesn't, is beneficial in its own right. Why? Because, I apologize if you can't see the script on the top. I assumed it would be able to. So I'll just read what it says. And the reason is, and that's what I'll provide to you today, is tools for deeper understanding of how you solve a problem. So even if it doesn't apply to your problem, just using causal tools, you'll have a better understanding of what you're working on and better understand your domain. And that will enable you to address a deceptively simple question in your data, which is why. Just one brief plug-in in the start. This talk is based on an article that I published in Towards Data Science about half a year ago. It was selected as a must-read, and it contains much more technical detail. This is kind of like more of an overview of what I discuss in the article. So here I assume that you all make data-driven decisions, and you're interested in going beyond correlations and associations and find causal meaning in what you're working on. I won't, it's a Saturday, I won't be showing any formulas or anything like that. I try to keep it as engaging as possible. Normally in my talks I show equations only if it adds benefit. And all these opinions are my own. I'm just doing this on my private time. Just a bit about me. I mentioned, so I've been doing data analysis for just about 20 years, and throughout most of my career, I did not know about causality and its importance. I came across it only in 2020, and it really changed the way I think. I don't always apply it, but I always try to see how I can benefit from just thinking in those terms, and that's the objective of this talk. And so I'll start from the end. The main takeaways is that it's my opinion that causal reasoning can enhance the scientific rigor of problem solving. And like I said, applicable or not, assessing causality is good for mental hygiene when you're thinking about your problem. And I'll manifest that in two tools that I'll talk about today. For some of you, it's an introduction. One is causal graphs. It's a way to visualize the problem you're trying to work on. And then another tool that's called identifiability is once you have that mapping of your problem, what causal questions can you ask and which you can't? Or maybe what data do you need to collect to address questions that you can't? And so that's called identifiability. So this is the agenda that I set for today. I'll start about just introducing, well, why are we actually interested in causality? And then I'll talk about a case study in which I realized where causality helped me solve for an apparent paradox that I had in a machine learning task. And then I'll introduce the two said tools, causal graphs, identifiability, and I'll end with a summary and provide resources that I found useful in my journey. So why are we actually interested in causality? Well, imagine that you are applying for a loan for a bank, let's say, for example, for a mortgage, and you get rejected. Well, the first thing that you want from the decision maker, if it's an automated bot or if it's from a human, is first of all, you want some sort of level of accountability. And so I raise this in finance, but you can measure like every domain, especially the highly regulated one, there is a level of accountability. Well, in order to be accountable, we need some sort of level of understanding. Is it because my credit score was too low, or the house of or the price of the house was too high? Well, what's the reason? Computer says what? Machine learning applications are doing really amazing things. Like we've all been impacted by large language models in various ways. But at the end of the day, the machine learning models do not have a true understanding of a system. We can get philosophical at the end, if you want, in the question time about the recent emergence of the thinking. But at the end of the day, machine learning is all about patterns. For example, I believe that the term machine learning, interpretable machine learning is a misnomer because the algorithms provide us with patterns, and us as analysts, we interpret those patterns. And I'll give you a very simple example. So this is fake data, but imagine that you have a treatment parameter and you have an outcome as a function of it. And you look at the data and you see an apparent positive correlation. So you can make a decision that, yeah, you want to increase treatment because then you'll improve your outcome. And of course, but now I'll shed some more information. Let's say for each dot here is an individual patient. So let's now say that we take into account their age and gender. Okay, and so we'll add that information by color coding it. And now any cohort now that you track, for example, Lisa Simpson will follow young females. You can see adding treatment actually decreases the result of the outcome. So you see the exact opposite trend. You might have run into this data without knowing that it is a thing, it has a name. It's called Simpson's paradox. And it's one of many apparent paradoxes that can come up when you're looking at correlations. You might be liable of misinterpreting your outcomes. And so that's something that like a machine would be blind to. If a machine doesn't know about age and gender, it would say, oh yeah, definitely increase the treatment. But you, as the domain expert, you have to feed what's necessary to make these sort of hard decisions. And so in causality, what we're doing, we're doing a shift of mindset. Instead of being passive observers of the data, in which we're asking what happened, we're actually being more active and asking what would happen if I do something. That's very abstract. We'll assume we'll talk about an example. But one thing we can do is we can frame questions like, what is the impact of some sort of intervention on an outcome? What's the impact of me registering to vote? That will increase my credit score, and hence I'll be more likely to get that loan I applied for. And what's the impact of taking aspirin on my headache? I'm sure in your domain, by the end of this talk, you'll be able to structure a lot of these questions once you have this sort of framework in mind. Of course, randomized control trials come into mind, where you're controlling for one subset of the population, and that's considered the gold standard in causality. But it does come, but there are a lot of challenges to it. For example, there are many reasons for that. I'll just highlight the first two. It could be expensive, just managing the logistics of this, but also feasibility. It might not be ethical. For example, if you're testing for the effects of smoking, you can't have people smoke for 10 years just to measure the effects of that. And so a lot of development of causality has been addressing what's called, sorry again, here on the bottom, it says observational data is more accessible. So that's what all of the industries are collecting without, controlling, for example. And so a lot of development in causality is coming up with sophisticated methods in order to understand that data and extract causality from observational data, stuff that they're collecting passively. And I think that that's a very powerful thing, not always possible. But I'll continue on the positive side. I'll demonstrate what's considered the poster child of causality. It's how we got to understand that smoking is harmful for us, and we're acting on it, for example, in adverts of cigarettes. So in the past, imagine yourself in the 1950s and they see a correlation. Well, how about causation? So the tobacco industry was a main player in politics back then, and you can imagine their scientists conveniently say, hey, there's this thing called DNA. We can't measure it now, right, before the Human Genome Project in 2000, still 1950s. We can't measure it, but maybe it causes both of them. And so even if there is a causal link between them, we have what's called the backdoor path over here, and so we can't establish this causation because of this backdoor path. And so in that sense, there's no way to solve this sort of problem. So if you have three parameters like this, if you can't measure this, you cannot solve for causality. So how did they actually solve for it before the Human Genome Project in the year 2000? Well, what they identify is something called mediator variable, which is the fact that when you smoke, you're actually depositing tar in your lung. And that's regardless of DNA. So there's no arrow going here. And so by having this mediator, you don't need to resolve for this backdoor path. You have what's called the front door path over here. And even if you didn't understand that, that doesn't matter for the purpose of this talk. But the important thing is that people who understand causality, they had this understanding of this mechanism, and by so they could convince policymakers to, say whatever the tobacco industry said, well, this is actually what's happening. Let's act on it. As society, we acted on it, and then we can start measuring the impact. The blue curve here is cigarettes sold per capita, and the red is lung cancer per population, and the different arrows are the different actions similar to this were acted upon, and we can see like the impact of these actions. And so this is putting on the rosiest picture of causality. That's why it's considered the poster child. We can go beyond correlations, and we can shift from what happened in our data to what would happen if we would reduce the tar due to smoking. So why aren't we seeing all these headlines about impacts of causality in society as we do when it comes to large language models? Well, the reason is causality is hard. This is a non-exhaustive list of all the reasons it can be hard. It requires many assumptions. Some questions are fundamentally unanswerable. And even if they are, it's more of a cognitive effort to understand, not only for the stakeholders, but also for the tech staff as well, and it's also more time-consuming. Hopefully, I'm starting to convince you to look into causality, and once you have this tool, you will be aware of the law of the instrument, in which what you have a hammer, you have to watch out not to cause everything to be a nail to chase. And so then the question arises, when do we actually need causal inference? And so I like this, I took this from a talk from Sean Taylor, who was actually mentioned earlier in the A/B testing talk, whoever attended upstairs, in which he talks about two camps, the always CI, that anything else is too simplistic, as opposed to the never CIs, which say, well, let's just keep things as simple as possible and solve problems. And for a long time, I agree with Sean's takeaway, which is that tools are just tools. Usefulness depends on the setting. And that was my frame of mind for a while, and I still agree to it to a certain extent, but I think that my mind has evolved. Soon I'll show you the example of why. And what it has evolved to is that causal inference is not a standard tool, but it is a frame of mind. It's my opinion that it may be useful to enhance interpretation of problem solving. And like I said, assessing causality in your problem, even if it's not applicable, is valuable in its own right. And in that sense, that's why I call causality as mental hygiene. And so now I'll briefly talk about an example use case at my work in which I found that I had an apparent paradox, and I managed to solve it by putting on a causality hat. And so what I had is, I won't go into specifics for confidential reasons, but just imagine a standard supervised machine learning task in which we want to predict for a target variable, and we had various explanatory inputs, x1, x2, etc. And for simplicity, I'll just focus on x2 as all the rest, and we get a score. And normally in our team, what we do is when we have a model, we want to compare it to some sort of baseline. And it's not a random baseline, but rather what would our stakeholder, for example, a clinician, what's the mental model that they have in our head? So just imagine that their mental model is they model for Y just based on x1, and what we're interested in, what's the added value of adding x2, etc. And notice that when we do our exploratory, all three of these there are correlations between them. And so when we look at the benchmark model, again, we're just predicting y just by x. Well, we get the same score. And this is something that really happened to me, and I'm looking at it, and like all these, they're all correlated, but I'm not getting a better score when I'm adding. Add insult to injury, machine learning told me that that x2 appears in my feature importances. And so I hope you can appreciate that this is an apparent paradox in machine learning. And it was hard for me to finish the project with this paradox. And so I asked for some more time. And I put on my causal hat in order to resolve this. So I won't go into the fine details. But at the end of the day, what I found is that x2 had a direct effect on y. But that was overshadowed by common cause x1. So I know it's a Saturday. It's just before lunch. And this is very abstract, and so that's why you want to use visual aids in order to explain this sort of thing. We had a target variable y. It's caused both by x1 and by x2. The width of the arrow determines by how much, but x2 is also impacted by x1. This is the same exact backdoor problem that I mentioned before. And so machine learning and regular statistics couldn't answer for that, but when I applied statistical reasoning, and this is something that you learn in the beginning of your journey of causality, how to think it that way. I managed to articulate. I had a vocabulary that I did not have before. And that enabled me to ignite the conversation of the utility of causality within the team. The picture over here is Judah Perel, who's considered the godfather of causality. He's a very quotable person. I have a few quotes of his throughout the talk. Causation is not merely an aspect of statistics, an addition to statistics, and I'm paraphrasing it as causal reasoning enhances the scientific rigor of problem solving. So that's my long-winded introduction to this talk. And now I'll go on into the two tools that I found very useful for assessing applicability of causality in projects. The first is causal graphs, and the second is identifiability. So causal graphs basically are a way to visualize the story behind the data. And that's a crucial aspect of causality, understanding what's called the data generation process. How do we get to obtain this data? What's the mechanism behind that? And so I actually showed you causal graphs before. Now I'll just formally introduce them. Each parameter is a node, and the arrows between them indicate the causal relationship, which parameter is listening to which. And this describes the data generation process. And for us as practitioners, it's a way to articulate both to ourselves and to our stakeholders and colleagues the underlying mechanisms in our opinion. So this is a very specific case. It's called a direct acyclic graph, or DAG for short. It's in these, we make sure that there's no cycles in them. And so it can be considered an oversimplification, so it might be in some cases, and we'll address that later. But basically, if your mechanism does work like this, then it highly simplifies the maths, and then you can actually extract causality from your system. And the reason for, and I won't get too much into detail, but basically it describes the joint conditional dependencies between the parameters, and this is all qualitative, but once you have data, that's something that you can actually test, because you have a DAG, you want to challenge it with your actual data. And so it is something that's testable, and that's one of the beauties of these mechanisms. So why is this useful? It's a way for us to interpret our data. I will argue also it's a better way for designing for experiments, and also you can transfer that knowledge, like not only to a colleague, but you can transfer it to like you could take it from, if somebody examines something in depth and you need only part of it, and it's in the literature and it's something that's been tested for, that's something that you can apply both on qualitative and then once you have data on a quantitative level as well. And so the main takeaway from these last few slides is that a key assumption of causality is you need a reliable DAG. Okay, and that's why it's also hard. I'm just checking on time. Because the next topic that I have here is how to build a DAG. When you do causality in a textbook, they provide DAGs for you, and that is straightforward. But in real life, of course, you have to actually build it. And so this is one of the many fields in the forefront of causality, something causal discovery. How do you go from your data to actually creating a DAG? And so, yeah, I think we're good on time. So, so basically, in order to do that, in order to create a DAG based on your parameters, you need some sort of level of domain expertise. If it's somebody in your company, or yourself, or somebody you work with, or it's scanning the literature. And that can be on a, qualitative level. And then in order to be quantitative, well, you have to actually gather the data to do so. And there's many ways of doing this. If the DAG is small, my preference is actually to do it manually. But once you get a lot of parameters, well, then you need an automated mechanism, and there are algorithms for that. But just for basic understanding, for kind of understanding like a small aspect, I prefer to do it manually. If anybody's interested, ask me at the question time. I have a few slides to talk about manual causal discovery. But now I'll try to keep it more high level, in which in order to do causal discovery, and I won't go into the detail of the algorithms. Again, I'm trying to keep it as high level as possible. But what you need not only is domain expertise, in order to assess how hard it's going to be, I came up with this spectrum of complexity, and it depends on how much control you have over your system. That will help you assess how likely can you do causality in your problem solving. So what do I mean by spectrum what do I mean by control? Well, let's look at the two different extremes. If you have full control of your parameters, for example, you're using synthetic data or simulated data, well, you turn the knobs, and so that means you have full control over it. The other side of the spectrum is you have no controls. It's fully observational, and you don't know the directionality of the relationships between the parameters. So then causality will be harder to implement in your environment. And of course, there's middle ground is if you have partial control. For example, randomized controlled trials or A/B tests where you have control of at least one or maybe more parameters. And so that's a spectrum of complexity, and then there's another axis to that is, well, are you dealing with iterative processes, like is it a function of time? And so, yeah, that will make it more challenging, and so common ways to do that, address that, is just have your parameter as a function of time, parameters affect each other, or if you have a steady state of your system at the end, then you'll have to wait for the steady state of your system. So just to summarize, this first tool of DAGs is that it's a very useful utility for causal interpretation of your data. I make the argument that by using it, you'll be able to create better experiments because you'll have this map in front of you, and you can realize the next section. You'll see which parameters are useful, which are not, and you can use this to transfer knowledge. Maybe somebody won't agree with a certain edge in your DAG, and it's a way to better communicate. One thing that I didn't talk about, and I do in my articles about this, is a lot of times you see people controlling for a lot of parameters without justifying it. DAGs are a way, it's beyond the scope of this talk, but it's a way for you to justify which parameters you should control and which parameters actually you should not control. So that is a thing that people should be aware of when they're controlling parameters. Something else that we talked about right now is the spectrum of complexity. Depends on how much control you have over your parameters, and that you can do it either manually, and once it's large, you want to use an algorithm. Okay, so let's say that you have a DAG, and let's say you tested it, you think it's reliable. That is the hardest stage. But let's say you've got there. Now you're wondering, well, what causal questions may I actually ask? And that's where identifiability comes into. Fun fact, no word checker likes this word, identifiability. It's only domain of causality we use that word. And so what is identifiability? It's effectively knowing what parameters are essential in order to answer which causal questions. So that might sound a bit abstract. I'll give an example. But basically what it enables you to do is identify which parameters are essential, which are by essential, I should be more specific, which are sufficient, which are needed, as opposed to which are absolutely necessary, but as important, which are unnecessary. And something being unnecessary, that could potentially reduce the budget of your data collection process. So just to bring home an example of what I mean by this is, let's go back to our poster child of causality. Let's try to solve for smoking and cancer. Let's say we have 4 parameters. Let's say we have a certain budget and we can go after these parameters. Let's quantify, let's use identifiability. And so the first step is identifying what are the minimal sets of parameters to answer this question. So I made so in causality, you learn that you can either do this, what's called backdoor channel. And so you need smoking, cancer, and DNA. You won't need tar. Or alternatively, you can just do this, use this front door path. So you'll need smoking, tar, and cancer, and you won't DNA, which is a good thing, because DNA, even in modern times, that's hard, both logistically and it's a very large, can be very expensive. And so that's why you want to identify, well, maybe I don't need this parameter. Maybe I can use this direction. That's what I mean by improving how we do experimentation, reducing costs. Okay, so once we identify once we define our minimum sets of parameters, well, let's say we collected the data, and now we identify what's then we can start to talk about sufficiency and necessity. So let's say that DNA and TAR are available. Let's say we're fortunate, we had the budget, we collected all four. Well, in order to do causality, well, you can go either route. So that means DNA and TAR are both sufficient, but they're not necessary because you always have the other, meaning you need at least one. But that might be a bit abstract, but let's make it more concrete. Let's say you don't have the budget to calculate DNA, or you cannot. So that means you only have this. So that means that TAR is both sufficient and it's necessary, meaning without that, you cannot answer for causality. Okay, so yeah. So I always find sufficiency and necessary kind of like a complicated issue, and this is kind of like how I wrap my head around it. You can think of identifiability basically as your recipe. It gives you it tells you what ingredients you need and what you have to do with them. What are the ingredients? The ingredients are the joint probabilities between the parameters. And by directions, I mean how do you organize them? So that's what they do in causality. I talked about backdoor channel, front door channel, and so that's how basically you organize your probability distributions in order to calculate. And I like this meme because basically what this is, it says this is what you want to measure. It's called the estimand, and then identifiability is it tells you what's your estimator, what parameters you actually need, how do you combine them together, and this is the estimate at the end. Hopefully, you get something that's reasonable. Yeah. So. Just to summarize identifiability, basically it tells you the minimum set of parameters you need to assess for causality, in which you list parameters as sufficient, necessary, and unnecessary. Potentially can help you with budgeting your experiment. And also, one should address, well, parameter availability. You have the difference between parameters you observed and those you haven't observed. And those that you haven't observed, well, they potentially could observe them, or they're unobservable. So if something's necessary and unobservable, well, that means you can't measure that causal effect. And so you have to rethink, well, how and what are you going to measure? Yeah, so now I'll just end with a few slides. I'll summarize what we talked about, and then I'll provide resources that I found useful for my causal journey. And so I like this quote popularized by Michael Bloomberg in the beginning of the data boom era, originally by a few consultants. If you can't measure it, you can't manage it, and you can't fix it. Hopefully by this stage you'll appreciate my paraphrasing. If you can't measure and articulate it, you can't fix it. And as Judah Perel says, data does not compensate for assumptions. We collect data, we have assumptions about that. And what we do in causality, we have this vocabulary in which we can actually test for these assumptions through graphs and the relationships between parameters. And that's something that you learn in causality. And so the main takeaway is that I made the argument that even if you cannot apply causality to its fullest to your problem set, just assessing its applicability is valuable in its own right, because you'll bring in more scientific rigor to how you're addressing a problem that you're trying to solve. And other benefits are, for example, you can improve the documentation and quantification of the domain you're looking at, and it's a way to improve the interpretation of your existing data. And also when it comes to designing experiments, like which parameters to collect, as you could see, as I mentioned before, maybe a parameter is not necessary in order to answer a causal question, and so you can bypass that. And of course, I mostly painted rosy pictures. It is hard. It's a lot of cognitive effort, and it's much more time-consuming in practice. And so this is just a summary of most of what I said before, in which I talked about the two main tools, DAGs as a way to visualize the data generation process, how you understand the data has been collected. And identifiability is a mechanism for you to take a DAG and say, well, what causal questions can I actually ask from the system? And so a few more slides. Let's go back to the beginning. Why are we actually interested in causality? So one last quote, I promise. If you cannot answer a question, if you cannot answer a question, you cannot ask. and you cannot ask a question you have no words for. Again, causality as that vocabulary that I was missing with statistics and machine learning in order to address that so-called machine learning paradox that I was looking at. I needed to put on my causal hat in order to address this. When you start learning about causality, you'll see something called the causal ladder. And so these are like 3 rungs of understanding of a system. Most of us start off, this is where I was for the first 15 years of my career, just seeing passively data, not acting on it. You know, I am pretty sure I ran into Simpson's paradox, didn't know it was a thing, and I solved it for myself. But by the time I had the machine learning paradox, I was smart enough actually to address it and go to like the next rung, which is called doing, being active participant, like looking at your data critically and acting upon that. And in the second rung, the headline is that you can do causal inference for cohorts. What's the impact of aspirin on all males between the age 30 and 40, for example, so as a cohort. So that's where RCTs come in, A/B tests. And then if you go into the field, you learn about do algebra. That's how you actually do the mathematical formalism. But the holy grail of causality is this top rung. It's called imagining, and that's causal inference for individuals. So it's how will this aspirin solve the headache, not for the whole cohort, but your cousin who's actually 34 years old. And so here you discuss something called counterinfactuals. That's like what-if statements, and this thing called structural causal models. What it is basically, where DAGs is qualitative relationship between the parameters. You're actually going to write the actual equations between them, and so you need a lot of trust in the system to get there. That's considered the holy grail. It's very hard to get to, but if you have this set up, then, for example, as I made the argument with the spectrum of complexity, if you have synthetic data, you might as well do that. Thank you. You could be there. And so a few more plugins from myself. I was very like intellectually stimulated by learning causality. I was very excited about it, and I did some writing and presenting on this topic. So I'll show you a few articles, and then I'll provide resources that I found useful as well. So this is the intro that I actually needed to causality. So this just talks about the fundamentals, the limitations of correlations, and also just the importance of justifying controlling for parameters when you should and when you should definitely not control for that. So that's the intro, kind of like I needed. So once you're ready, you're ready to commit and put your toe in the water. I wrote this article as the first, in order to, the first step in causality is mastering this Simpson's paradox. And I promise you, once you understand this, and it took me 3 weekends actually to understand Simpson's paradox to its fullest. It will change how you look at data forever. I do promise you that. One more thing is that I started this journey on causality, but I also realized, just as a side note, I've been using topics from information theory, entropy, Kale divergence, mutual information. I didn't really understand mutual information, so I dedicated the past few months writing a few articles on that. So it started as one article, became a 5-part series. So I recommend starting with this summary of the first 3, information theory for people in a hurry. So I'll stop with all my plugins. So these resources I found very useful. The first 2 are by Judah Perl, a popular book, The Book of Why. And if you want to, and this is a really good textbook to start looking into equations I highly recommend that. And if you want to apply in Python, I highly recommend this one by Alexander Molak as well. This course by Brady Neal is everything you would want. It's clearly explained, it's thorough, and it's free. I highly recommend that as well. And once you're ready to apply in your work environment, I highly recommend this talk by Dimitra. I see Danhanbi actually are one of the advertisers here. So I love this visual of hers contrasting between traditional machine learning and causal, where here you can see she talks about the causal graphs, and here she talks about identifiability, which I presented today. You got it? Okay, cool. I see people taking photographs. And if you're ready to play around with yourself, sorry about that. If not come out good. So I highly recommend Daggerty as on a browser. You can just explore creating DAGs and interpreting them. So it's a very useful tool. If you're Pythonic, then I highly recommend DoY, part of the environment of PyY, and they have a very good four steps of causal inference, which is fairly rigorous, especially this refutation step. So I highly recommend looking into that. And many thanks to James Baker, who actually did all the doodles. That was not me. So with that, thank you for your time.
Thanks, Eyal. We've got time for a few questions.
Hello. Yeah.
Hi.
Thank you very much for your talk. It was really insightful. I would like to ask you a question. It's more like a recommendation about building DAGs. So I'm a senior data scientist at JLR, and I've been through this journey of trying to build a DAG to try to see what variables was impacting sales. So we start with this idea, and then we started using business knowledge, talking to stakeholders to build this DAG. But the problem was we didn't know when to stop.
Yeah.
The DAG was getting bigger and bigger and bigger and having more nodes. And we managed to undag the DAG because we started seeing cycles. And a DAG is a directed acyclic graph. So we had cyclic relationships in this DAG as well. So we couldn't progress because, one, we didn't know when to stop. Because if you keep asking the business, they would just say, this is relevant, so it grows indefinitely. And also we couldn't have a DAG because we saw cyclic relationships as well. So what would you recommend in terms of building a DAG using business knowledge, as I tried to do and failed miserably?
Oh, that's a very good question. Full honesty, I haven't been at that stage that you have, so you sound like a much more advanced stage than I have been. I've been, building on my own and looking at it, but I have, my understanding is you're doing exactly what you should be doing. I did speak with experts, and they did say that it is a lot of back and forth, and it sounds like you have been doing that. You didn't assume that you go into one meeting and you have all the answers. And I do not have an answer for you. It sounds like you're in an advanced stage, and I congratulate you for actually doing that. And I apologize to disappoint you, but I'd be interested in hearing more offline later.
Hi, thank you for your talk. I have a question about the automated graph discovery bit. So there are a bunch of algorithms that promise to sort of learn a DAG from the data, but oftentimes they do not consider sort of the conditional independence relations that are required. And my question is do you know of a way to sort of from this automated step, find, sorry, I need to think of what I'm actually trying to ask. Because basically we get the DAG that was found through statistical methods.
Yeah.
And it's all a result of an optimization process. But it does take into account all of the identifiability conditions or the conditional independence requirements. So when I try to do this kind of work, I feel there is a split there.
Yeah.
Where we have a DAG, but if we try to validate it, it comes back as invalid. And then how do we move on from there?
Yeah. Okay. So I'm glad the first two questions are very challenging questions, very advanced questions. So I'm just wondering, you're saying the algorithm you're using, they don't test for conditional independence? I'm quite surprised about that because I thought that was the bread and butter of.
It's the no tiers algorithm.
Okay. No tiers.
What it does is it kind of turns the whole DAG discovery. So the no tiers algorithm turns the graph discovery problem into a continuous optimization problem because they kind of encode the rule of acyclicity of the graph into a continuous function.
Okay.
And it's really cool, and it gives you a graph, and you show that to the business, and they go oh, there's all of these really super interesting relationships. But then if you try to validate the conditional independence requirements between the nodes in the graph, then you find out actually there's a lot of super correlated variables here, and this DAG looks kind of invalid.
Okay.
So you kind of end up in a situation where the business goes oh, this is really interesting, but then you look deeper into it and you're actually this is not that valid.
Okay, that's why I started off mentioning that I like doing it by hand. When I have small programs, because that's what I look for. I look for conditional independence, and that's how I built it. So yeah, I'd have to learn more about that mechanism and why they're optimizing without doing that, because it sounds like bread and butter of causal discovery.
Yeah, there's several there's different tools that
Yeah.
address. So there's different tools that address steps of that causal pipeline, but so far there isn't something that does everything.
Yeah.
That we can have an end-to-end solution. That seems to be a bit far off into the future. You also mentioned the due calculus, and I was looking and it would be great if there was an automated way to have a DAG do the due calculus inference over it and just get the answer, but that's we're a bit far off from that. So it's an exciting field because there's a lot of development.
I could just mention for those who aren't those who aren't familiar with the field that we've been going into a bit deep here, but basically one limitation of causal discovery is that it's limited in what it can do, and that's where a lot of domain expertise comes in. I think I have a slide on this in which and it's on my slide deck for those who are interested. These are the three most basic DAGs, like chains, forks, and inverted forks. And one of the interesting things about causality is that a machine can find the difference between this and this as a group, but it cannot find, these all have the same relation. When it comes to conditional probabilities, they all have the same relationships. It's called the Markov equivalence for those who go into it. And so, again, the limitation of causal discovery is you can distinguish this from these, but from these three, you cannot know. A machine just based on data cannot know, and that's why you want to apply domain expertise of a human being in there. So the human needs to be in the loop at some stage in causal discovery. So, yeah.
Cool. Let's thank Eyal again.